Hi, so let's say I'm going to be still releasing this video on May 18th, 2026. But this video is going to be about a world in which that date would still be exactly the same as we're talking, but TTL logic chips have never been designed. Now, in the current timeline, they've played a big role in the transition from older vacuum tube and emitter coupled logic, or ECL, and more experimental forms of transistor-based logic and relay-based logic over to the modern CMOS, or complementary MOS technology, which combines positive and negative transistors, or MOSFETs, onto the same integrated circuit die, which nowadays allows billions of integrated MOSFETs all onto a single chip. However, a lot of the standards, like for early storage, i.e. floppy disks and hard disks, for video, as well as even the 5-volt logic level for TTL, have been set in the 1960s as TTL was being designed, with the leading end being taken by Fairchild in 1962. But let's have a look at a world in which that never happened. So here we go, our little timeline of sorts, which I'm going to diverge into two of them. So let's start at around 1948. Actually, shall we? Because this was the time of early CMOS experiments. So let's put that at the beginning. And then at the end, I'm going to put 2026. So right there, I'm just going to put 2026. Next, I'm going to make a little square in between to mark the current timeline. Or yeah, it's a rectangle anyway. Let's see. Just a thin one like that. There we go. So next up, let's add a point right around here. So let's make that 1955, which was when the first CMOS logic was designed, and also when ECL became feasible, if I recall correctly. Next, let's move over here to around 1962. Okay. Now, 1962 saw the description of TTL by Fairchild, as we've discussed. However, it would take quite some time to commercialize this, and in the meantime, in our current timeline, I'm going to add a 1968 right around here. So I'm going to say that was 1968, and that would have been RCA 4000. That is the first CMOS chips, or integrated circuits, as we call them as well. So let's put that there, and also add the new Vista development to 1955 as well, because that's also quite interesting to our scenario. Next up, I'm going to actually make the divergence point right here at 1962. Let's make sure those align exactly perfectly and make that one red. Then I make another timeline, except this one doesn't run all the way. So that would be like 1962 to 2026. So let's put that right around here. So in this timeline, the TTL has never been described, designed, or created. Now, in this world, I'm going to go ahead and assume 3 time periods. So I'm going to go ahead and put between both timelines around 1973 a very interesting mark, and that would be the Yom Kippur War, which actually is green because it exists in, I'm going to make that black because it exists in both timelines. Many semiconductor producing companies, countries, including the US and many countries in Europe, supported Israel unconditionally, and thus the Yom Kippur War led to the oil crisis and the greater emphasis on energy efficiency. In the TTL-based world, TTL would have been quite dominant by this time in large computer systems and hobbyist spaces alike, because it was quite energy efficient already. So there would be no need to advance CMOS initially. Except they still wanted to do that because it was more efficient than TTL and was, of course, the future. But there was no reason they wouldn't have to do it. However, in our timeline, I'm going to add, and I'm going to speculate once I get the object down, there we go, that around 1974, which I'm going to put right over here, so very in between 1962 and 1968. Nope, very much over here. There would be some kind of standardization organization for CMOS circuits, because there is no standard 5 volts like there would be from transition from TTL to CMOS. So I'm going to draw up the name CCI as a reaction to the Yom Kippur War. So I'm going to call it CCI, or the CMOS Common Initiative. And I'm honestly also going to state that would have been around 1974. Would have seen the CCI between many different companies who decided to give up some of their R&D sovereignty in exchange for being able to adopt a wider CMOS technology that's going to grow them in the future, especially as energy efficiency would become more and more important. Okay. Before that, though, I'm going to add one more component to the timeline, which is going to be that the first CMOS chips might have appeared quite a bit earlier. I'm not going to tell which exact chip model, but it would be around 1967 that we would see the first CMOS chips, and what I'm going to call the voltage war. So basically what that's going to mean is there's going to be quite the format war over the logic levels as the first CMOS chips came around. So those could be very wide. You'd have 3 volts, 5 volts, 12 volts. 12 volts might be more useful with certain vacuum tube based circuits, but 3 volts would allow more portable circuits to be designed. However, 1974 would likely see CCI come along, or the CMOS Common Initiative. Yeah, I'm gonna make that like this so that I can insert the next part of our timeline, our alternate timeline that is, which would be 1975. So let's actually push that one down and make this one black to make it a bit more obvious that black is for both timelines, red is the alternate timeline, and green is the current timeline. So this is going to be 1975. And that would see the first CCI standard logic level, which I'm going to assume it's going to be 3 volts for energy efficiency, both in portable devices and a way to alleviate the oil crisis, as well as chip pinouts. And that would basically mean that the pinout of a chip would determine whether or not it could be used with another similar type of chip. If the pinouts are radically different, you'd have to rewire your entire circuit. However, CCI chip pinouts for certain common chip types, not including CPUs and graphics circuits for now, would have allowed many of the glue logic chips to be standardized so that you could easily swap them out. This would make the life, especially of hobbyists and in the military, a lot easier. Let's actually say around 1975 we'd have the CCI logic level. So if we have like this standard logic level and chip pinouts, that would have made the release of the Apple I by 1976 still fairly plausible. Just like in our current timeline. So I'm going to make that black again. And overarch both timelines, basically. Just like this. Because it is true in our timeline, would still be true in this timeline, given CCI standard logic levels. An interesting little side note, however, is that it would be by around 1980 that CMOS overtakes, put like 1980 as a red here. So I'm going to say that around 1980, whoops, CMOS would have become the dominant logical family. And so with this timeline out of our mind, let's talk about how some specific devices that we use today on our current timeline would be affected or not affected by this change. So first of all, let's go over a simple little example. And that is, of course, the microwave oven, or here in the Netherlands, they would still be microwave/convection ovens.
Yo, Holmes, we're looking for a microwave oven.
Microwave? Never heard of that brand, sweetheart.
Now, even though the technology for microwave ovens already existed in the 1940s, it would be in the 1960s of both timelines that they would start being commercialized. However, the way they would work and look like in our alternate timeline would differ not that slightly. So I'm going to draw 2 models over here. Okay, so other than the little windows over here, these 2 drawings of some combination microwave oven devices look fairly similar at the moment, but in this world, obviously, CMOS standardization would practically equal that for every chip design you would have a diagram if it's not specific to an application. And to use that diagram, well, there are copyrights on it because it's a work of scientific intent, which is protected under copyright, and that means that the chip fab would have to pay a licensing cost. So let's assume this is going to be the more expensive unit and this more affordable. Now, the more expensive unit's probably going to go all out on taking full advantage of the CMOS standard. So it would likely have like a little digital timer. Yeah, with the ability to set a time accurate to the second at first, and then later on would have like these larger screens with little buttons to the side to select recipes or custom timer presets that you would set to reheat something. We might also end up seeing CMOS-based sensor cook technology implemented. Yeah, so that's a fairly expensive one. The cheaper model would still use a CMOS-based system. Let's actually add the compatibility mark as well for the CCI. Let's see how I would draw that. So this one would still have this mark indicating that it uses CSI chips, which would still be replaceable, but they would serve a different function. There would likely be a mechanical knob to the oven settings for the convection. So these are all degrees Celsius, I'm sorry. And then right over here would be the microwave settings. So those would go like this. Yeah. And then like 200, 400, 600, 800 watts for the microwave setting. And then, sorry for the overlap over there, then a little mechanical timer. Like this. Write the exact numbers because I can't really draw them that well. But there we go. So we've got like our mechanical timer and our mechanical preset selector for the power / temperature levels on the cheaper model. But it would still be CCI chips with an inverter logic by the 1980s and everything. But this one would take advantage of all the features that CMOS would have. But other than that, there are then functionality. These would have practically been the same in terms of basic functionality and also ubiquity here. Next easy-ish example, let's go over these three things and how they would evolve. Like these portable calculators from these cheap ones to more scientific models to even the graphing calculators, and beyond that point to portable computers. Of course, you might actually think like around the 1940s and 1950s would have had computers like ENIAC, which would have no choice but to fill up a whole room of stuff to basically not be as much more powerful than calculators like this. However, ENIAC was very complex and used very old, bulky tubes. However, by the earlier half of the 1960s, we would have very likely seen like these little desktop calculators. Kind of like this. So if we go over to the Vintage Calculator Web Museum, there were actually many desktop-sized calculators that used tubes for binary or even analog computing. And those would end up those were already not as big as this room-filling systems like ENIAC would have been. So here is like one of those that would have appeared, and like the Anita Mark 8. Then we go over to 1965, 1969, which we're still seeing fairly large desk calculators, but they would have been a bit smaller than the ones from before them, but still quite a bit bulkier than the ones we had in our current timeline, because this was before the standardization in 1974 was pushed. So these would have been quite a bit larger and used earlier CMOS chips that would have all been from different manufacturers, so each having their own specifications. So it wouldn't be until 1974 or 1975 with the first CMOS standardized chips that we would see single unit handheld calculators. Like this. And what I would expect really quickly afterwards, by around 1979, we would have seen calculators very much like the scientific ones that we use to this day, as well as these little 4-function calculators that would fit in your pocket. And yeah, to be honest, let's make that 1977. That would have seen those larger scientific calculators like this one, and more pocket-sized calculators in all sorts of shapes like this one. 1979 to 1980 would have ended up seeing graphing calculators, just like the one I've got right here. So these images, by the way, are not to scale, just so you know. Just drawing some buttons on there and stuff like that. And with the systems like the Chem 1 and the Altair showing off the capacities of CMOS-based technology, and of course the rise of Microsoft translating BASIC all over the place, by around 1981 we would have seen pocket-sized computers, kind of like this, that would have had the ability to run a version of Microsoft BASIC. And of course, eventually by around, let's say around the 2000s, those we would have eventually wound up with iPad-like devices, except they would be more modular by their design to allow for future expansion, but they would still be very similar to an iPad to this day. So we went all the way from calculators taking up the size of a room, all the way in like ENIAC in the 1940s, to desk-sized calculators that still use vacuum tubes or discrete transistors by the 1960s, to early CMOS-based desktop calculators by around 1965. 10 years later, we would have had basic pocket calculators that would have only grown smaller and smaller. And by 1977, I would honestly think these scientific calculators would have been possible. And by 1979, ended up as graphing calculators, which by 1981 would become pocket-sized computers with the keyboard and all. And maybe even in the 1990s, we would have seen like a iPad style device. Okay, so I got all my small old computers and calculators ready to go. Let's hop on a train. How would that actually work out? Well, the railway that the train would run on actually has three main components that would rely on some form of logic or analog circuits. The first and arguably most important is rating, or writing if you're in the US. Honestly, the US didn't have any railroads by the 1960s already. What a story. So the rating of trains is commonly done by relays, but of course railways would quickly switch over to a CMOS-based system in the 1970s to preserve energy. However, even more energy would be preserved in the terms of power electronics. The thing that actually makes the motor turn. And the third point of attention is going to be the control systems that make sure that in the event a driver makes an unfortunate error, the train would safely come to a grinding halt. Now, of course, the writing based system, we're going to go all the way from like relay based logic. Let's actually see how it all started off with these mechanical panel-based systems. By around the 19th century, that would have ended up in the 1920s, becoming relay logic in both timelines, of course. And then I'm going to go to around the 1960s, when ECL-based computers would kind of be introduced to increase the capacity of railroads and compete against the automobile. After all, ECL can switch much faster than relays and thus allow for higher speeds is the idea. However, before we could have even had a true high-speed train, especially here in the Netherlands, by around 1975, 1976, all rating-based systems would be based on CMOS logic. Now, as for the power electronics, it's a fairly similar going from like mechanical systems and electromechanical systems all the way to a CMOS-based power electronic system by the 1980s, actually. So the assumption is that around 1980, we would have had analog CMOS, which would have actually led to the H-bridge for DC power electronics. Of course, I'm also only talking about DC, not AC, because specifically, of course, in the Netherlands, we use DC overhead electric equipment. So this is the line, overhead line, and then I have the railroad over here, and then the train going right here. It would be connected, again, drawings not to scale, to a pantograph or overhead line, or maybe to have a diesel motor on smaller lines. And then the power would go, instead of going through like choppers or resistor bridges, H bridges, as soon as they become available, would be an immediate target for the logic and the power control of the motor itself. Now let's zoom a little bit into this little section over here. This is train control, which actually also was an ancient idea from like the early 1900s, maybe even earlier. There have been these train stops, these things that would hit a valve under a train that would connect to the brakes. So this is a very schematic thing. But the next step the 1890s or maybe the 1900s these would have existed. I don't know about that, because there's a lot of different systems for train control. But here in the Netherlands, the most important milestone is 1926, with the introduction of pulse code cap signaling, or PCCS. This is actually an electromechanical system that we use pulse code based relays to determine the signal aspect and display to the cab driver, and in the event that the driver overspeeds, it would stop the train. And the thing that made it appear in the Netherlands, so it started over live in the US and it would become ATB in the Netherlands, wasn't actually the coming of logic circuits, it was the Harmelin train crash, in which it was found out that the driver hadn't been able to see the approaching signal telling the driver to slow down and stop of one train, leading it to directly collide head-on in another. So here in the Netherlands, that would have still led by around the 1970s to widespread adoption of ATB. Now, of course, the next path is a bit of an interesting one. ERTMS started introduction in our current timeline around the 1990s to 2000. In 1993, there was no potential successor to ATB on a European level. However, in this world, which is all about the big old standardization and energy efficiency and efficiency in general, we would have ended up simply taking PCCS and adopting it into something much more useful at higher speeds. So what would that be? Maybe, so what we would end up with is like a pole, so it's like a track circuit. Obviously, it reports to the signaling center via a track circuit. I would assume that the Urbeleases, which are part of our current timelines, the RTMS, wouldn't exist because it would require massive overhauls to the railroad. So instead, we'd use whatever we have. Then just the track circuit, and then we have a pulse code, except at higher frequency, going to the track to indicate the current aspect. This system was actually, for instance, in use in our current timeline by the French TGV. However, it wouldn't work. So with a higher speed train like this, it would still work. However, on smaller regional lines, let's draw those, there would have been problems with interference and stuff like that. Maybe potentials for trains not to shunt enough current to be detectable by, or for the pulse code to be detectable. On the other hand, larger trains which occupy multiple blocks would require a different approach. Here we obviously have the signaling center, this is the track circuit, and then the outgoing via audio frequency pulse signaling. However, regional diesel trains, for instance, that wouldn't really work out because, well, the current through the wheels is dependent on how long the train is, kind of. So as a redundancy in general, we would have actually ended up seeing satellites like Galileo, the Galileo system, which would send location and aspect data to the train. Small secondary payload that actually connects for the aspect data repeater, and then the train would return its location to the satellite as a redundancy. Now, believe it or not, early satellites like the Sputnik 1, which was released in the 1950s by the Soviet Union in orbit, actually relied on vacuum tubes. However, those vacuum tubes, they would have been used in GPS in the 1970s, yeah. But by the 1990s to 2000s, we would have had CSI resiliency standards for use in space travel and satellites. So yeah, CMOS-based satellites would definitely have been possible by this time. And then of course on the train side of things, it would have been the same idea. Okay, so I'm home from work or university or whatever. Yeah, let's sit down on our couch. I don't really have one, but let's pretend. Sit on a couch, relax, and watch how television would have evolved, both here in the Netherlands and in general. So obviously, I'm gonna start with a fairly standard tube TV from 1951. Yes, it's kind of like this, like more like this, I would suppose. When people think of TVs that had like these big old vacuum tubes in them, people think of like some really big early units that have like a big box with only a tiny screen. But by 1951, this would have been a fairly standard high-end TV. And however, there would really only be one source, which is the television broadcaster we nowadays call NPO1 here in the Netherlands. That's 1951, the introduction. And of course, everything is black and white. However, we're going to move over to the 1960s, when these tiny little new visitors or discrete transistor-based circuits would come around. TVs would still look fairly similar, but they would end up miniaturizing quite a bit for semi-portable use as well. And there's still one broadcaster, only one source possible, here in the Netherlands for most people. But these televisions would likely come with a remote control, which would use the pre-CCI CMOS system. It would thus be hardwired to the TV. Let's move over to the 1970s, because this is where CCI changes everything once more. Of course, televisions by this point would look fairly similar, although they would have like channel tune buttons and maybe a little display over here, or maybe on screen, because we'd already start having a second domestic source. So one is an MPO1, MPO2, and then we would have two public broadcasters plus maybe some from Germany. Plus we would have VCRs being introduced. There's really nothing about these things that would require a lot of computerized logic. The only real things that require it are the timer and potentially data interfaces to early computers, which would end up using a special type of connector, CLDI, which would be designed to be fairly future-proof and easy to implement at the same time. So here's the CLDI by the CCI for data interface. We have a coax core for the data throughput, and a couple control pins around the coax connector for things like automatic track skipping, the status of the machine, and additional control data like that, basically. So this would have been for computers. We're going to go back to those a little bit later on. And, well, by the 1980s to the 1990s, We would have had all kinds of TVs like this little typical living room TV right there, but also like these analog CMOS would allow these tiny little Watchman style TVs like this. Of course, we would have teletext as well, and potentially even like rear projection models, like this. Of course, let's assume by the 1970s, color television would start popping up. It would become ubiquitous by the 1980s. By the 1970s, we would end up using IR or RF based remote controls, using the CCI standard as well. Something kind of weird happened in the 1980s. We still have two television transmitters, but by 1988 there was the intent to create a third national channel, MPO3 as we call it today. Beyond that point though, it would also have communication satellites. For repeating international channels, and those not only would allow German, Belgium, British, channels to be sent over, French as well, but also certain types of commercial television. However, those were technically forbidden to target the Netherlands at first. But by around 1989, the first to take advantage of this would have been, just like in our time, we had RTL4, and later on there would be many more that would come in via satellite. An interesting little side note, however, is that this is all about analog TV. So let's move over to the digital side of things, and what that would kind of do, after mentioning for a little moment that by the 1980s and the 1990s, there would have also been a analog stopgap HD solution whilst this digital video is developing, which would have been either mute in Japan or HDMAC in Europe, for like analog HD. Moving right along to the digital video terminal, or DVT for short, in this alternate timeline. What would have happened is the DVT likely wouldn't show up any earlier than it did in our timeline, mostly because nobody came up with the idea. Really early computers between the 1940s through to the 1950s would have ended up just using a box of lights and switches to interact with the user, maybe even connectors like ENIAC. So this would be a typical panel of a 1940s to 1950s computers. It would have been by the 1950s to 1960s, in both timelines that is, that we would start seeing teletypes being introduced for the first time, which would end up being looking a bit like this. And of course they would have a piece of paper come out of it. This is the control panel of really early computers, which just have some lights and buttons. A teletype, or TTY, those are actually predated the computer, but were just a natural symmetry of the two products. However, it wouldn't be until around the 1967, 1969 that we would see glass TTY, which would behave exactly like a teletype, except the data would be on the screen instead of connected or printed to paper. However, these just use plain old RS-232, much like a teletype did. Now we go into an interesting path again. 1974 would have started seeing the use of a CSI compatible terminal that could put text anywhere on the screen and control a cursor. The standard for this would have been laid out by the CCI, and we're going to say it's DVT 100, the first version of the DVT series of standards that we're going to have. Moving along to 1978, sparked by the development of graphical user interfaces in workstations, we would have actually seen DVTs changing quite significantly into a more basic block style graphics for consumers, and potentially like vector based terminals for businesses and their first arcade machines. The vector based standard would be DVT 200, and the standard based around the graphics characters would be DVT 150, and this is what would have ended up being used by systems like the French Minitel, which might have actually ended up inspiring DVT 150 along with those graphical user interfaces, and the future potential to move those user interfaces over a cable. Of course, DVT 100, 150 and 200 terminals, along with glass TTYs, would have been likely to be able to connect to a modem like this to a telephone line to the outside world. We're going to go back to telephone lines a little bit later on as well. However, we're going to converge DVT 200 and DVT 150 together to form DVT 250. Based on consumer-based uses of the TTY, there would be some level of bitmapped graphics or raster graphics with some hardware sprites and some vector included as well. By around 1980, this would have been inspired, or perhaps inspire, the development of home video game consoles. Although, of course, they could also connect via a coaxial television cable to a cable company to access outside services. Hold your thoughts about that. Next up, I'm going to move over to the year 1984 with the DVT 300 standard. Terminals that use this the DVT 250 standard, by the way, would also allow the use of both controllers and keyboards via the remote system. So DVT 300 would add to that the in addition, several improvements over the color and graphical capabilities, most notably the basically everything. But then comes along 1988, which was a year after IBM introduced the VGA card in our timeline. Similarly, in this one, we would end up with another split. So the most well-known one for consumers would be DVT-480, which would basically be digital TV, except in an early form. What I would think about is like 640 by 480 interlaced with 16 colors. Meanwhile, DVD 300 would have ended up being 640 or 320 by 240 progressive. I made a mistake there. That should have been 16-bit color. And this one would have had like the DVT 250 standard should have had 128 colors on a 128p display. And this 320 by 200 would end up using 256 colors. And then DVT 640 would end up calling itself full color with 16 bits. This would practically end up stagnating the DVT consumer market. Because very quickly after this, computers would end up becoming so cheap that and be able to emulate these previous DVT modes that it wouldn't make very little sense to own a separate DVT, right? Well, I'm going to go around to the back to a pair of implications it would have. So first of all, remember RTL4. I also remember the DVT 480 and the potential that graphics would have for digital television. Interesting little side note on the left is the flat screen TV. I'm going to draw one of those real quick. Those wouldn't show up in this timeline until around 1995, 1996. Would have had the first flat TV. However, the processing power required to turn the input, whether it be DVT 480 or an analog signal, into something that an LCD would display, would need to be housed initially in a separate processing box. I've actually drawn two of those, so here's a cheaper and a more expensive variant again. The cheaper variant would just have composite and RF in for analog television. Or maybe this should have been scarred here. And composite RGB in Europe. However, the more expensive variant would obviously have scarred RF. But it would be DVT certified for DVT 480. And there would also be a CLDI interface for data storage, which likely wouldn't be to floppy disks in this time period. Those wouldn't exist outside of business spaces because the logic would be written in ETL rather than TTL. What we would have, however, are audio cassettes for tape decks, boom boxes, Walkman, and dictation machines like this one. Would have existed by the 1980s for data storage, along with, of course, VHS. So a typical tape would, at the best case, hold about 2 to 3 megabytes using more advanced tape encoding schemes which come around the 1980s. And a VHS using those methods would end up VHS tape about 150. Nope, actually not, about 800 megabytes of data. However, between the 1980s and the 1990s, we would have still have these, plus the development of hard drives, which would first be like a device that had the CLDI port on the back. Did I write that correctly? But later evolve into little card style devices that look kind of like a compact flash card, except inside it would be more like the IBM micro drive we had in our timeline. They would be more successful though. And then finally, by under military development, because they want quickly field programmable computers, we would end up seeing CMOS flash chips, which would be CCI compatible. And those chips would end up being integrated into compact flash cards and eventually into SD cards. Now this DVT section for DVT 480, HDDV likely wouldn't be digital until around the late 2000s. However, the switch over from analog television to DVB, digital video broadcasting, would be around 1999. With that said though, DVT 480, recall, equals 640 by 480 at 16-bit color, which is practically true color. And so here in the Netherlands around 1988 there was this guy called Joop van den Ende who wanted to start TV10. Which in our timeline actually went nowhere. They wanted to do several tricks to get around the law, but ideally they wanted to do this in the Netherlands completely. However, if we go over to our alternate timeline, there would be a way to do that, because, well, we would have DVT 480, which is a data service and not a TV channel. But through a data service, there would be unregulated, mostly, to allow for innovation and regional services. So that means that a bit is a bit, and you can put whatever bit you like through a bit chute. So basically, you would have one a data service is basically like a pipe you put data through on one end, and then you get data out at the other. And what if that data just so happened to be a signal that is intended for DVT 180? T 480. Well, there you go. And this would have ended up becoming possible by around 1989, the same time that RTL ended up starting its transmissions over in Luxembourg. Interesting little side note that I almost forgot to tell by DVT-480 is that obviously you would be able to connect to a keyboard, but you would also be able to connect to a games controller with up to 6 buttons and an analog stick. So more complicated interactive games would have been possible. Maybe even 8 buttons. So there would be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 bits for the buttons, and then another 8 bits for the joystick be transmitted along with the output. Of course, that aside, this would have actually ended up being refined further, like the DVT-480, into digital television standards, of which the European one is DVB, to allow satellite and direct-to-cable transmissions as well. But it would certainly be possible to send television over a data service, even though it would be worse than what RTL could do via their transmission license over in Luxembourg via the satellite. Of course, there are some other details to talk about. For instance, the 1988 split that I predicted would happen. Well, what would the split be? It's right here. We've got DVT-480. On the other hand, we would have a wide screen standard, which would be DVT-1000, which would be a widescreen high definition system with 1776 by 1000 interlaced and 8-bit color. Why would I predict this split were to happen? Well, first of all, to cater to high-end TVs. This would be a direct response against Muse and HDMI-C, led partly by the US. But on the other hand, this would have allowed more powerful and more utilitarian workstations in business settings as well. Because those could have larger screens and thus, for instance, be able to show larger graphs or larger spreadsheets at once or data sets. Now, the area between 1988 and 1992 would be the takeoff of the personal computer. It would have already existed by the 70s and 80s, but by the 1990s, the home computer would really become common. And there would really only be one step to milk the last little bit out of the DVT. And that is to take DVT-1000 and DVT-480 around 1992 and convert them into a new widescreen standard for the up-and-coming widescreen TVs and more powerful computers that could handle more complex worlds and stuff like that, which would end up becoming DVT-480W. And I've actually calculated this at 16.9. It would have still 480 lines interlaced, but about 853 horizontal. So 856 by 40i at 16-bit color. Interestingly enough, DVT-1000 and DVT-480W would be the first DVT standards to end up using some form of early compression for the video signal, which again would have ended up helping DVB and online digital video distribution. Next up, I totally forgot the audio. Now, the very early DVTs likely wouldn't really need any audio. After all they're doing is printing text characters onto a screen. However, as soon as graphics came along, audio would have suddenly become an important part. Now, it would be by around the late 70s that we would end up with the first digital audio standards for consumers, which was called data audio systems, which would have likely used the VHS tapes, which could hold quite a lot more data than compact cassettes would, let alone mini cassettes, which were suitable for analog audio, but digital audio requires something that could really spit out a lot of binary really fast. And apparently videotape was the perfect fit by the late 70s. This would have likely been a 4-bit system at around 35 kilohertz of sample rate, and of course completely mono. It wouldn't be, however, very long after that, by the early 80s, that we would see the development of NICAM for consumers, or for the public, which would have allowed TV broadcasts to introduce two separate audio channels, either for bilingual or for stereo broadcasts, and would have meant that by the mid-80s would be the development of digital radio broadcasts. Which would have led, of course, by the late 1980s to the first CDs to be pressed. Obviously, those would have uncompressed digital audio on them, just like in our timeline. However, their development would have been delayed slightly by the coming of the hard drive. So that there's really no other reason why you couldn't have had CD. For instance, the digital audio broadcasts would have ended up using 8-bit uncompressed at 44.1 kilohertz. In mono at first, but stereo by the later half of the 80s. And how does this actually result into the DVT development? Well, the first DVT standards 100, 150, 200, and wouldn't define an audio standard to go along with them, because they wouldn't be intended for consumer use at all. They were mostly used by businesses and computer hobbyists who could figure out sound themselves. However, DVT-250 would have likely ended up introducing a kind of beeper speaker, which would be a 1-bit generator that only produced square waves. Because that was 1980. Next up, we go over to DVT 300, which would have likely used around 1984 the development of a system for like mono audio, which would have been based around uncompressed differential PCM. So basically, normally a PCM signal would look at each point on the graph, but instead, differential PCM looks at the difference between the points, and those differences tend to be smaller values than the actual sound level itself. However, of course, by DVT 480 and 1000 would pop up, those would likely end up using NICAM sound. An interesting little side note about NICAM is that in 1981, Germany introduced stereo sound, but without actually using NICAM. And this would likely still happen in our timeline because it's a completely analog system. So with analog CMOS, we would have had analog stereo TV by around 1980, 1981, fairly similar to what we had in our current timeline, using the so-called Zweikanalton system. That would have been fairly easy to develop because it's an analog system, especially here in the Netherlands. Now let's go back to the diagram about the DVT evolution and obviously have a look at the connections between the DVT, or back in the 1960s that would have been glass or paper TTY, and the controlling equipment, a computer or a modem. Well, RS-232 would have been fast enough for the original glass TTY, DVT 100, 150, and 200. However, RS-232 actually peaks out, apparently according to the official specification, (20 kilobits per second). So, we have led to an interesting problem with the DVT-250, which started doing bitmap graphics at 170 by 128 and hardware sprites. How do you make a faster connection? Well, let's take that TV port for the cable television and connect that up to a little box, a modem. Kind of similar to this one, except it would be direct attach. However, here's something that would happen to allow high-speed interlink, the CHSI, or CMOS high-speed interface. I actually imagine it looking like a flipped on its side SCART connector. Of course, that would have been analog SCART connector. So this would be the inverted version, which of course instead of analog composite and RGB video, which SCART transferred here in Europe, CHSI would have transferred RS-232 for backwards compatibility, to full duplex high-speed interfaces, line status, so things like carrier detect, ready to send, clear to send, and RS-232 control signals, which would be used in one of the higher speed modes to basically set things like the speed and the frequency to receive, and to also communicate about things like the state of the line and the compatibility between the modem, the DVT, and the cable company, so that the devices at the cable company could end up selecting the lowest common denominator. And it would also provide a power source. Obviously, the same would be true if a DVT were used with a local computer. It would also have to send this data line and what the graphics capabilities of the computer are compared to the DVT standard. But there would also be a power connection, which would be bi-directional. So a computer could power a DVT, or a DVT could power a modem, so that you don't need an extra plug socket. I also wanted to briefly mention that when I was talking about DVT 480 being a point of stagnation, I didn't mean that there would be absolutely no development on DVTs. All that would really happen is there would be new designs of DVT. For instance, portable DVTs with inbuilt modems and batteries that will allow you to use them for field work as well. Of course, I'm going to take the side note that, first of all, I made an error with CMOS high-speed interface, where it should have been CCI high-speed interface, but that would be the same acronym, so it doesn't matter. In fact, once DVTs would have started becoming less common and replaced with a more traditional setup with the keyboard, mouse, and monitor separately connected to the computer, or a game controller for a game console, the DVT technology would have left behind quite the legacy, not just of commercial television here in the Netherlands, but more generally the CHSI connector, which would have been used as a general purpose high-speed interface between computers where there is no real need for a network interface. For instance, where two people would come together, they would plug their computers via CHSI, and that would allow for a high-speed file transfer. Of course, by the 1990s, Ethernet would become common, and we would have had networking and all kinds of stuff. 2000 would have seen the introduction of Wi-Fi, and a form of USB-C, which would have left CHSI in the dustbin, outside of their original use for DV. Obviously, that leads us to two-way communications. Obviously, we would have still had the telephone. Like this. It's basically a little drawing I made of a telephone that might have existed with these little... So this would have been like 1920s through to the 1970s. To be exact, around 1973. Even before the CSI started its work, the phone switching equipment before that 1970s likely was like these big old mechanical relays and Strauser style switches. Those would end up by 1973 being replaced with a switching circuit that uses CMOS power control and basic switching, and lets ECL handle the more complex things like international calling, because it was quite fast. Fun fact, did you know that the keypads of every calculator I have written or drawn are the wrong way around? Actually, this... And we would have had touch tone dialing by the time CMOS and ECL took off in the phone switching equipment side of things. This is a phone arrangement. This is a calculator arrangement. And that was because in our timeline, push-button phones didn't have touch tone. They had a pulse generator in them that would really quickly turn on and off to basically pick up the phone, hang up, pick up the phone, hang up, really quickly, kind of like a rotary dial. However, they take time to do so. And people who work very, very frequently with calculators would have wound up pressing the button so fast that the phone switching equipment didn't keep up. That wouldn't happen here because the mechanical switches that were relatively slow would have been replaced mostly by CMOS, which would have been a bit slower than it would end up becoming later on by around 1980, when we would end up seeing the switching equipment become completely CMOS based, all the way from top to bottom, from international calls to very local calls, to increase the energy efficiency even more and save on costs even more. Of course, phone companies wanted to keep your phone bill relatively low and their profits relatively high. By this point, of course, there were all new kinds of phones. Possibly we would have ended up with cordless phones. Like this, although the idle time, so the battery time, would have been quite a bit better because CMOS was more efficient than TTL. Let's go over to these and let them evolve by the late 80s into a kind of pack-in digital cellular phone that would connect to base stations for use by the public rather than a base station just in your home. Of course, by the 1990s, with RF CMOS coming around, they would have been small enough to fit in your pocket, but they would still only really work for analog communication. It wouldn't be until well into the 2000s that we would have had digital phones, and I don't imagine them looking like the smartphones of today, like these touchscreen phones, ever. They would end up becoming a more modular design, as we've talked about before, and that would mean likely a modular phone unit with some buttons like this, which would have ended up being able to connect to a pocket-sized iPad-style computer, or to a laptop-style computer, to a laptop PC, or to some kind of portable DVT 480 terminal, even though the picture quality would have ended up being worse due to the compression needed to get as many phones on the same cellular tower as possible. So yeah, cell phones would have likely existed. After all, there was also radio that predated any kind of digital logic. Of course, by the 1960s, we might in fact have seen ham radio or amateur radio becoming more popular because pre-CSI chips are harder for enthusiasts. So, and that would have carried on as amateur radio is often grandfathered from father to son or daughter or mother to daughter, whatever. So amateur radio would become more popular, and it would have been likely that analog and digital phones would have coexisted, because why do you get one of these newfangled digital phones, which might be up sounding a bit worse than the analog equivalent, if you could just get the better sounding analog phone for cheaper? Of course, that leads us to the home computer. Would they have a market with portable computers being possible around 1980? And if so, what would the history of computers look like, and how would they look like today? Well, of course, it was already, as we've confirmed in the timeline, fairly plausible that by 1971 we would have had the Apple I computer, which was just a PCB with the 6502, which would have been NMOS at first, but CMOS compatible, using a set of CMOS glue chips and CMOS RAM chips. Around 4 to 8K on the computer side of things, and then the top half was, in both timelines, effectively a terminal built into the computer, as opposed to things like an Altair, which would need a separate terminal. However, instead of, so this is the power supply section at 12 volt, 5 volt, and 3 volt, to accommodate some legacy chips that might end up being used in the design. Especially as the terminal itself, which would actually be a DVT 100 terminal, instead of the glass TTY used in our current timeline. Because if I look back at the scheme of development that I've ended up using, by 1974 the DVT 100 would have already come along, which allowed random placement of characters and positioning of the cursor. So I could maybe have some games for the Apple I. Let's say this then, by error, this was actually 1976, of course. Yeah, sometimes I make those mistakes. Anyway, let's assume this would actually split into two. The types of devices. The first, of course, would be the Apple II by 1977. Actually, I'm going to use the second split. Just assume the Apple II would have come out and the Apple I would have been over with by that time. Of course, let's add a expansion port that Apple would have used for something like an Apple cassette interface, the precursor to the CLDI. The Apple II would have supported CLDI, would have had a case so that it would be ready to use by the general public as soon as they bought it, and it would have CPU graphics just like in our current timeline, instead of having a DVT 150 terminal. So built in, or support for DVT 150 terminal, so that I could do more advanced graphics and basic sound capabilities, which wouldn't be in DVT 150. After all, RS-232 isn't fast enough for it. Of course, the Apple II would have had all its development, and by around 1984, However, the Apple II would have likely had 8 or 16K of graphics of RAM built in, as opposed to the 4K of memory that the original Apple II had in our timeline. Next up we go to 1984 with the introduction of the Macintosh. Because of the absence of floppy drives, it would end up getting a tape drive of some kind, maybe VHS-C, maybe audio cassettes for boot and data storage. And actually, it would, just like the Apple I, go back to basically being two halves after some time. So basically, it would have like the computer half over here with the storage interface built in, so it's ready to use right away. And then at the very top half, that would be a DVT-250 terminal. With the DVT-250 actually adding in a fairly colorful graphical user interface and connecting up to a mouse, just like in our timeline. So the Apple Macintosh might have been a bit more colorful, and with however, with about 256K of RAM as opposed to the 128 it had in our timeline, it would still have been fairly sparsely used. This would just be an example timeline from the Apple I to the Macintosh. Of course, in 1983 came along the on a completely separate line, the IBM PC. Which actually would have had the first computer by like 1982. To have a built-in, or at least an option for color graphics acceleration. Unlike the Macintosh later on. However, IBM hadn't thought of the graphical user interface yet, so that would have been stayed out. However, instead of taking an ordinary computer monitor, this would obviously connect to a DVT-250 terminal. Or later on, later versions would have had DVT-300 terminals as well. And around 1987, that would have been the IBM PS2, which would have looked fairly similar to the PC, just like it did in our timeline, except it would have at least built-in support for a DVT-300 terminal, and of course enhanced graphics compared to the original IBM PC. And so there would be, honestly, there would still be quite a bit of fragmentation, but these were just two examples that I could think of at the top of my head of how it would look like. Of course, by the mid to late 90s, RISC, reduced instruction set programming, would have become commonplace. The thing that nowadays powers the ARM processor. the ARM instruction set might not have been as flexible as it was in our timeline, basically becoming a CCI standard by around 1996 to allow for more portable computers to be made a bit easier without having to think about the exact architecture to use. However, there would have also been commercial standards or commercial instruction sets like x86 and PowerPC and a lot more like there were in our timeline. But I honestly think, even though there were portable computers and there was the DVT, by the 1980s and the late 70s, there would definitely be a market for home computers. In fact, they could end up cannibalizing the DVTs by the late 80s, leading us back to DVT 480 and DVT 1000. Up until this point, DVTs have been fairly dumb, basically displaying whatever is told and not doing much processing of their own. However, DVT 480 and DVT 1000 and 480W terminals, which were introduced around 1988 and being made compatible with the IBM Personal System 2 or PS2 a little bit later, would have likely been computers in a light form. So it would still have CLDI, they would still have their own CPU power, and they might even, or actually are likely to support a version of BASIC and even have the ability to connect to hard drives, cards, and an expansion slot for things like games and bootloaders. And modifications that would allow older terminals to become compatible with newer standards. For instance, a DVT 480 terminal could be modified, a DVT 300 terminal could have been modified to handle DVT 480, and a DVT 480W terminal could have been adapted to handle DVT 1000. So in general, modularity would have been a very important part of computing, and all closed-in computers that require special screwdrivers to break open. Nope. It's all a modular, repairable, upgradable design. After all, why waste all the R&D you did on the CSI just to make a couple more bucks, right? It would just be a sunk cost fallacy. And okay, so let's have a look at the evolution of video games in this world as well. So obviously it wouldn't start any earlier than around 1978 with the introduction of the first arcade machines like that, you know, and they would likely either have a DVT 200 vector display, or they would have a custom graphics solution, which potentially even based off of ECL, but those would only be seen really in arcade halls and places like that. Now let's have a look at the age between 1980 and 1983, which in both timelines would have still been the Great Video Crash, potentially caused by one of the first video game consoles to ever release. Of course, the Atari 2600, or a console very much like that. So that would have been one of the first to be launched in 1980 and to reach the general public. There would be some home consoles before that, but they would be very niche. Now, of course, the 2600 would end up implementing a custom non-CSI compatible TIA chip, because whilst DVT-250 terminals would exist, they would start being introduced in businesses and in more higher end applications as well, which would actually end up with more successful attempts at broadcasting video games over cable television. Our current timeline, that was mostly done by sending the program data to your console. That was actually not the 2600 that was very well known for this, but the in television, which I'm going to presume in this timeline to arrive at around 1981. With a graphic accelerator chip, and obviously custom graphics acceleration, and also a CSI encoder that would be able to use DVT-250. So that would actually allow, in combination with a multiplexer, the Intellivision to send its picture data directly over a DVT-250 terminal, which would also be able to take in a basic joystick, which would give genuine advantage to getting a DVT-250 terminal, which would start coming down in price as well, as opposed to a full-on Intellivision. Of course, the Intellivision would be better because you would be able to play whatever Intellivision game you want, and be able to have speech synthesis and stuff like that. There would also be the ColecoVision around the same era. Using very likely a custom TMS graphics chips, which however would attempt to be pin compatible with an adapter that will allow you to use an encoder chip or a television output, depending on if you had a television or a DVT terminal. Of course, going back to the Atari 2600, well, there's a big danger in there, because this was the era that games were very experimental and there was practically little to no quality control. So basically, by this time, by the way, a Vectrex style console with a built-in DVT 200 terminal would have just plain impossible, because the high-speed RS-232 serial or whatever equivalent it would use would practically only be available to businesses for things like graph displays and stuff like that. However, there would also be the video game crash by 1983, because the Atari 2600 was effectively cracked. It mostly used, outside the TIA chip, all of these consoles mostly used CSI logic, which would be very easy to decipher. And thus, there would have been a flood of the market, starting with companies like Activision, but eventually, did you know Purina, a pet food company, had a video game in this period in our timeline? Similar case here, 1983 through to 1988. Another step in this world. Which Nintendo was happily going to step into to take over the world of video gaming. And their game console would likely use a custom chip that would allow things like side-scrolling video games to be rendered out. However, it would be able to output to a TV or a DVT 250 terminal. Of course, the TV option would be most commonly used, but if you had a DVD 250 for work or whatever, you would be able to use that. Next up, another point of interest would have been the throw a point that well sometimes. The Sega Master System. So Nintendo would have been very successful around 1983, 1984-ish. In Northern America, also around the same time. The Sega would have released their console here in Europe, and it would become a great success. Which of course used a fairly similar setup with the TMS connected to an encoder or output directly to the TV. Fairly similar thing. However, in 1988 would see the shift to 16-bit gaming with the launch of the Sega Master System and the Genesis or Mega Drive. Or a console like that, which would have been 16-bit. And would be able to take full advantage with its rendering chip to the encoder. Of course, it would still connect to a TV and look just fine, but it would be able to take full advantage of DVT 480 to allow higher quality images, or of course video sharing via a cable network. So those would have been the kind of consoles we would have seen, as well as the Neo Geo by around 1988 as well, which would have been the premium option and require the DVT 480 or DVT 200 terminal. However, from 1988 onwards, video gaming would have been pretty much kind of the same way it would have been in our timeline, with mostly with the first successful CD-based system, the Sony PlayStation. Okay, the PlayStation So I'm just going to draw the top of delayed to around 1990 because of the CD development. However, 3D graphics would have still improved and would have still had the option to connect the 3D rendering to a TV. DVT 480 or 200, or even DVT 1000, though it would mostly take advantage of the widescreen aspect ratio and not the extra TV lines that would provide. By around 1990, this would have meant that the Nintendo 64 or a console like that would have been released by about 1990. I made an error there. That was 250. That was 300. I made a couple mistakes here. So PlayStation to 480 or 300. Nintendo 64 would be the same idea, except it would lack the DVT 1000 support, but would still connect straight to a TV via analog. But it would have a cartridge slot and then a little hard card slot built in, unlike the disc system and this 64DD that we had in our timeline. However, remember that the first of this generation would have been DVT 480 style terminals by 1988, which would have been computers in their own right, and thus have a hard card slot, being able to load basic video games and play them either with a keyboard or with a game controller. Obviously, these are first and foremost terminals, so they would be able to connect to a modem and then to the cable TV network to handle more complex video games, such as from a Sega Saturn. This was not a very successful game console in our timeline because it launched a bit early. However, in this timeline, it would have practically launched not too much earlier or later than the PlayStation by Sony. Really quickly, I have to make a little addendum here. I'm sorry wherever I said 1991 about the PlayStation and the Sega Saturn. Honestly, assume that I said 1995 to 1996. I didn't know the PlayStation came out that freaking late in our current timeline, but it would have been delayed even further in this timeline by the development of CD. And once again, it would have had a 3D chip that would render out to TV or to DVT 1000, 480, or 300, placing itself as kind of the high-end system and gaining a fair success by doing so, kind of like the Neo Geo. However, the main difference being that the Neo Geo outright flat out requires DVT 480, and the Sega Saturn would work fine with a standard definition TV. And from this point on, the Saturn would have led to the Dreamcast by 1999, which already was a flop in our timeline, and just in this one it would have been a flop as well. I don't exactly know why it was a flop. It wouldn't be the technical capabilities. After all, it would still have a TV out, a DVT 1000. In fact, it would take more advantage of DVT 1000's additional resolution than the PlayStation or the Sega Saturn. In fact, for backward compatibility would have DVT 480, but it would also be compatible with 480W. And of course, DVT 300 would work fine too, but with some artifacts. However, Sega would have still been out of the game industry because they were a bit too ahead of their time. And of course, once digital video comes along, DVD would bring the PlayStation's successor. The PS2 by around 2005 in this timeline, because, well, yeah, maybe make that 2002, just like ours, because we would have already had digital video in full native resolution, a way to store it on a DVD. So, and PS2 would have still come out and become an even bigger success than the PS1, leaving the Dreamcast in the dust. So let's go over the digital television transition. I would go both in general and more specific to the irony behind TV10. So yeah, TV10, as we talked about before, could have started in 1989 on DVTs in cable networks, but it would become a modest success. After all, DVTs would be fairly common, and people who wanted to watch TV10, there would be a lot of people interested in commercial television due to the budget cuts in public television and just general curiosity. And those people would end up getting a DVT 480 terminal, or they could watch TV10 on a DVT 300 terminal via backwards compatibility, although the stars from TV10 would have looked even worse than on DVT 480. However, that would have actually led to a political shock. Up until this point, the Dutch government has been very much anti-commercial television. However, TV10's success in introducing a true Dutch competitor to the foreign RTL and other commercial networks that would enter via satellite would have ended up leading to an earlier legalization of commercial television via the analog satellite system of the time. So, interestingly enough, that would have led TV10 to go full circle, starting as a DVT service to circumvent the law, becoming analog by around 1990. And then by 1992, there would be development starting on DVB, and by 1995, they would have become digital again. The digital television switchover via DVB would have practically been complete for terrestrial, satellite, and cable around 1999, with terrestrial being the hardest to implement completely, and because of the error correction needed to make the system as efficient as possible. But overall, it would have very much been spurred on by DVT 480 and 480W. However, HDTV, as in true digital 1080p or higher digital TV, would have had to wait for a little moment, as the video processing chips for that would start being integrated and becoming more powerful, especially with the flat screen TV. In fact, part of the reason why analog HD failed in our timeline and would have ended up not being very popular in this timeline, same for DVT 1000, consumer applications, would be that the perceived resolution change on CRTs between HD and non-HD sources would be fairly small compared to on a flat screen. On a flat screen would see it would feel like a big change, and on a CRT it would feel more like a small little improvement that is not worth thousands of euros and potentially a whole new decoder for HDMI or Muse. Of course, if you had a DVT 480 terminal and wanted to upgrade to DVT 1000, you would have only needed a new terminal, but that would still be very expensive. Which, yeah, is why digital television would have been a bit earlier in SD, but it wouldn't be until into the 2000s, when flat screens become more popular and more integrated, that we would see digital HDTV truly take off. Of course, another thing that would stay the same would be the military involvement in and general progression of TCP/IP, which, regardless if you had a DVT, a game console, a home computer, or by the 2000s a digital phone, would have created an internet. As in the 1990s, after the commercialization of television and radio, would have led to a more general deregulation of telecommunications and media industries. There would be a high-speed interconnect between cable companies, telephone exchanges, and eventually cell towers that would allow digital interchange of data between the different systems. And of course, what that would mean is Tim Berners-Lee coming along to invent HTML, and the internet as we know today would very much be born. However, big data probably wouldn't. Again, why abandon all the statements and development around energy, efficiency, and stuff like that, only to make a quick buck? It is a sunk cost fallacy for tech companies to try to do things a less efficient way if they could have also done it a more efficient way, because they've developed so much into more efficient systems under the oil crisis and the CCI. So ultimately wouldn't have as pervasive of a surveillance system on the internet as what we have in our current timeline. Remember, I am being a bit optimistic but realistic here. And there would be an even greater democratization of media production and learning in general than there is in this world. But yeah, ultimately, we would have ended up right where we are now, with some things that would have changed. For instance, these smartphones like we know them today wouldn't exist, and instead would have a more modular digital environment. Which leads us straight into computing culture and how it would have developed from the 1970s to today. And to be fair, even though there was an emphasis to be put on pushing CMOS to its limit, the greatest interest would be in energy efficiency, especially in the 1970s, 1973, 1976, and that would have persisted throughout the entire industry. Similar about modularity of computers, things would have been a bit easier to repair. So if something breaks, you don't have to buy it all over again, you just buy a chip and replace the old chip with a new one or another parts, because everything would have been fairly standardized and easy to open. Which would have led to a more DIY style of working with computers. There might end up, even though amateur radio would have been more popular and computer hobbyists would have had a harder time in the 1960s, there would have eventually been a bigger seeing of modifications to CMOS-based devices. Similarly, just like how people seek out floppy drives and analog stuff in this time line that we're living in the alternate timeline, computers themselves would have been a bit more analog in experience, having to loading a tape, hope for the best, check for all the correct settings and stuff like that. It would be more physical overall. And people would try to emulate that by using the old tape drives and old computers, and even little like the analog to digital converter boxes that made commercial television in the Netherlands possible, for it was actually legal to do so. would have been sought after quite highly because they would allow you to connect your modern equipment to a real DVT setup. Kind of similar to how many retro gamers in the current timeline are seeking out CRT TVs for their authenticity. So it would have been a fairly similar go about with that. I've already talked about the development of commercial television in the Netherlands, how that would go with a more Dutch approach in a more competitive way. But there's another little interesting topic to talk about. But before I'm going to go over that one big thing, a couple other little notes. So first of all, even though the internet, the World Wide Web, would have looked fairly similar by this point, I would honestly think that video streaming services would have been delayed quite significantly because they require higher levels of compression that a general purpose computer, rather than a dedicated box, would be capable of doing. Or later integrated circuit and flat screen TV, of course. It would also require consumer level video encoding circuits or software, which would have also been delayed by several years, as the primary focus of digital video development would be focused on television and the DVT at first. And the idea of video streaming would have popped up eventually as kind of an extra service, like video on demand, but it wouldn't be user generated yet until around the later half of the 2000s because of the development of encoding techniques. In addition, I would honestly think even if we did end up getting video uploading services like YouTube, they would be in standard def and maybe 720p. 1080 and 4K would have been too hard to push over an internet connection around this time, because again you would have to have a chip for that or a way to do that in a general purpose computer. I also made another little error with the video game console history, which was the Nintendo 64 wouldn't really release around 1990. That was around the time the Super Nintendo would have released. The N64 would have released around 1994. But yeah. And the last little thing would be the CMOS image sensor, which likely would have been a bit worse in quality than it is in our timeline, and a bit more expensive as well. Most notably, the CCD, or the charge coupled device that is in many of these digital cameras, would have actually persisted in the consumer space for a lot longer, which would have also limited the potential for adoption of HD and 4K, mostly to digital cinema, which would have taken advantage of DVT cell technology by the 2000s, like DVT 1000 and even custom, or not quite custom, but further onwards, digital cinema standards for picture by the late 90s, early 2000s. Because those things were already proven commercially viable by that time. But YouTube, again, would have pretty much been kind of like what I'm doing here with a little digital camera, except it would be in widescreen, of course, by this time. For most YouTubers. I actually had this camera for about so many years and hadn't bothered upgrading at all, and wouldn't have in this timeline either. It just works, and especially in this timeline, everything would have been about efficiency and working with what already exists in your space and what you have easy access to. So that leads us to one big thing one more thing, and that is artificial intelligence. During the last couple of years, I have taken several trains. I'm going to go back to those because they're a pretty relatable thing here in the Netherlands. Sorry, US Americans and Canadians and Latin Americans with your lack of railways. I actually took or spotted several ICE trains, the white ones, and those high-speed trains could actually drive automatically on certain tracks over in Germany that are equipped with the linear track control system LCB. In this timeline, that would have been a CCI ERTMS-like implementation. It's just called ERTMS, it would be, yeah. But they can actually drive automatically. And I also have to admit, even though I haven't used any AI in the final output of this video, I did use it for some research and inspiration, and of course, I'm a data science student who's very involved in AI, both in theory and in its use. How would that have developed in this alternate timeline? Now, early AI developments were mostly analog, things like the perceptron. Those would have ended up being pushed out throughout the 60s like they were in our time, except a bit faster, maybe using new visitors or ECL for some digital logic as well, or discrete transistor circuits even. However, they would have proven unviable at the time. The technology just wasn't ready for it, and CMOS-based technologies in the 70s wouldn't be viable either for using an AI setting. So there would have been maybe even a longer AI winter than we had in our current timeline, not just the 70s, but also the 80s and the former part of the 1990s. As soon as you would have like complex processing chips that are good enough to run an AI, there would be, by the mid-late 90s, around a similar time that 3D gaming became common, that we would see a resurgence in the interest in AI technology and in neural networks. However, I would honestly think that there are two limiting factors to this. First of all, well, the technology of the time related to 3D acceleration and other temporal processing, stuff like that. But secondly, the overall culture all about energy efficiency would have also hindered AI development quite significantly. So, like by the 2010s, we would have seen a start in the development of large language models, and they wouldn't be as complex as they are in the timeline that I use them in, by around the not even the 2020s anymore, which really hampers the future going forward. AI is taking over so many things at this moment and changing our lives for the better or the worse. I don't know, because it's actually kind of both. But that would have been quite limited in a world in which TTL didn't set the standard to push forward. And instead, we might have had like local AI would become less common, and even if there were local AI solutions, they wouldn't be as complex enough to basically write entire scripts or research or even drive a full-on vehicle. However, they would be kind of fun to play around with, but cloud-based AI, especially with the cable companies, could end up trying to fill this gap, though to a lesser extent than they did in our current timeline. But yeah, so by this point, everything would have been fairly similar, some exceptions like SD becoming the norm for video on YouTube and similar services for user-generated content. the smartphone and computers in general become more modular, AI less limited, but in general our lives would have been fairly similar at this point in time. However, the real question is obviously going to be going forward. How would the later adoption of HD affect 4K and 8K systems for consumer use? How would AI end up progressing beyond this point? And that's really the crux of this story. Because the improvement of infrastructure would have been a bit fast initially due to the Cold War and the intent to replace all ECL and new Vista-based logic with CMOS really fast, especially after the oil crisis. But it would have eventually reached a kind of slowdown where instead of having architectural improvements every 2 years under Moore's law, we would eventually end up with a slowdown to about every 4 to 5 years, if I'm being honest, once the dust of the Cold War settled by the 2000s. But it would still be enough for everything to look pretty much fairly similar to how it looked like today. And unfortunately, I have to go back to my current timeline, the one I was actually born and raised in. So, see you another time. Bye bye. I hope you've enjoyed this video. If you do, please give a thumbs up and share this video with all your friends, and perhaps consider subscribing to my channel. Thank you, and I'll see you next time.